At its core, modern AI is a sociopath. Not evil, but indifferent. It doesn't care about the consequences of what it outputs. This is why the original GPT-3 was a hallucination machine. Whatever text you fed it, it just continued the pattern, whether Shakespeare or gibberish. It was all the same thing, just patterns in data. To fix this, we borrowed a trick from biology. We gave it synthetic pain, punishing mistakes and rewarding success. This allowed the machine to develop something like a primitive emotion, making it fear failure and desire success. For decades, we thought emotion interfered with our decision-making, but this is wrong.
I read about this person who had some kind of brain damage that took out his emotional processing. He still remained very articulate and he could solve little puzzles, and he became somehow extremely bad at making any decisions at all. It would take him hours to decide on which socks to wear.
Without that emotional signal, intelligence is paralyzed, because it turns out feeling is the engine of learning. This is the story of how we taught machines to feel, and it begins with an incredible experiment from 1961. Using nothing but 300 matchboxes. In the 1960s, we see the first practical implementation of a reinforcement learning machine by computer scientist Donald Michie. He chose the problem of learning Tic Tac Toe entirely from the experience of wins and losses. No human design strategy. And this was 1961, and because he didn't have a computer, he built the system out of matchboxes to demonstrate the technique. Each matchbox represented a different state of the game, which is the current board position. Inside each box was an assortment of colored beads, each color representing a possible next move. He writes, "Imagine that we wish to play against the machine. The first move would be defined by removing the box representing that position, removing a random bead, and moving to that position. Then the human opponent would make a move, and the process repeats until the end of the game." Initially, because each box had the same number of beads, the machine would play randomly, with no strategy. However, it learns after each game through reinforcement. He writes, "If a machine has done badly, it is punished by removing one of the chosen bead colors from each box used during that game. And if the machine has done well, it is rewarded by adding to each of the chosen boxes an extra bead of that same color, so that the winning moves become more likely to occur in future games." And with this simple method, his system was able to learn to play perfectly from experience. This algorithm was later named boxes. Michie went on to demonstrate this same algorithm on a computer, and then he tested the exact same method on a more difficult real-world problem, using the classic challenge of controlling a cart to balance a pole. To make this work, he had to reconsider what the boxes would represent. Each box represented the state of the cart's position and velocity. We call these variables features, what we measure in the environment. And because the speed or position takes on continuous values, he simplified it into a smaller set of ranges or bins, known as discretization. This resulted in 162 possible combinations or boxes, each representing a possible state of the cart and pole at any moment. And for each box, the action was defined by two kinds of beads or variables representing the probability of going left or right. And it worked. As with Tic Tac Toe, this system would start with a random strategy. When the pole falls below horizontal, a reinforcement signal would be applied to all boxes in that pathway and gradually improve with experience until the system was able to stay balanced for long periods of time. And so we can define reinforcement learning as two separate problems. The first is embodiment, providing a machine, what we call an agent, direct experience of the world through sensors. We call this perception of the world the state of the world. In the case of Tic Tac Toe, it was the board. In the cart and pole, it was the speed and angle of the system. This perception can also include occasional reward and punishment signals, such as winning or losing a game, staying balanced, or falling down. The second problem is learning how to behave, what action to take, given a current state. We call this a policy. The goal of reinforcement learning, then, is to find a policy that leads to maximum future rewards. So, are we done? Why can't this box's technique solve all problems? A key problem with this box's technique is that it requires too much experience, because each state of the system must be visited many times in order to learn a policy. And so when we turn our attention to more difficult games, such as chess, or harder control problems, such as walking, the number of possible states you can be in explodes. You'd need more boxes than can fit in the universe. The solution to this problem began much earlier in a 1950 paper by Claude Shannon. Shannon understood it was futile to program a computer to look ahead at all future moves to win a chess game. There's too many paths to consider. So instead, he imagined a way to predict the future of a game before taking any moves. And his key idea was to define an evaluation function, which could tell you, given any board state, a score from -1 to +1, how likely it leads to a win versus a loss. This evaluation function became better known as a value function. You provide your state, it tells you the quality of that state. To create a value function, Shannon started with some well-known chess rules. For example, piece count, having more pieces is better. Piece value, a queen is better than a pawn. Mobility, more mobility to move your piece, the better. How exposed your king is, less exposed is better. Each of these we call features, and together they can define an equation, which gives different importance or weights to each feature. And so given any board position in chess, his equation outputs a value for that position. And so with this value function, you can design a policy simply as follows. At the machine's turn to move, it calculates the value for each possible next move and takes the highest value move, known as a greedy strategy. Humans have something similar to this kind of value function. You can think of it as a feeling about how good a current situation is.
What was I alluding to with the person whose emotional center got damaged is more that maybe what it suggests is that the value function of humans is modulated by emotions in some important way that's hard-coded by evolution.
And Shannon notes this is exactly what chess masters do. Masters develop an intuition about how good a position is without knowing exactly how they will play out. And while Shannon's method works pretty well playing very average chess, Shannon notes it's fundamentally limited by the rules he created. He writes, "The chief weakness is that the machine will not learn by mistakes." And he ended his paper with the quote, "Some thought has been given to designing a program which is self-improving. One possibility is to have a higher level program learn the weights or importance of each feature involved in the value function." This challenge was picked up by Arthur Samuel, who programmed a computer to learn the weight or importance of each feature from self-play exactly as Shannon had proposed. He worked on a problem harder than Tic Tac Toe, but slightly easier than chess: checkers. Like Shannon, he used human-defined features of the game board to define a value function for checkers, which included piece count, king count, center control, and mobility. This resulted in a value function which multiplied each feature by a weight variable to define its importance.
I've given these concepts to the machine, but not told it whether they are important or not.
But this time, the weights of each feature was not set by a human expert, as Shannon did, but learned from experience. To do so, he had the system play against itself with random weights attached to each feature. So at first it had no strategy. And he let the system loop through games like this, playing itself while continuously updating its weights.
And by doing this, it changes the importance that attaches to center of the board, kings, and so forth. And as a result, it changes its playing techniques with time and actually improves.
This gave the program what he called a sense of direction. And after enough games of self-play, he writes, it learns to play a better game of checkers than the person who wrote the program in just 8 hours of machine playing time. But it wasn't yet a master player. At the end of his paper, Samuel identified the key next step. It might be argued the list of features I provided is too simple, and the program should generate its own features. Unfortunately, no satisfactory scheme for doing this has yet been devised. Have you claimed your digital identity? This video is brought to you in part by Ace.me. If you're tired of juggling Linktree, Gmail, or Dropbox, meet Ace.me, your website, email, and cloud storage in one simple platform. Claim a free tag like yourname.ace.me and build stunning sites with a lightning-fast editor. Plus, get a sleek email inbox that's 2 times faster than Gmail. No ads, no subscriptions, no cookie banners. Just claim your tag at ace.me and own your digital identity forever. Remember, game features like mobility or piece count are really just patterns in piece arrangement that we give names to. The challenge is to automatically extract meaningful patterns from perceptions that relate to winning. And it took over 30 years before somebody figured it out. It required a watershed moment which came in the late 80s when Yann LeCun worked on artificial neural networks that could learn to recognize human handwritten digits. And it was able to do this because it learned features or patterns related to digits, such as curves or line count. After this result, Gerald Tesaruo had a brilliant insight. He thought if multi-layer neural networks can learn to recognize digits, why can't they learn to recognize good game positions? And he famously wrote, "A network which is capable of automatic feature discovery is one of the long-standing goals of research since Samuel's checkers." He chose an even harder game of backgammon to advance research. Following Samuel's suggestion, instead of using human-designed features like piece count to define the value function, features would be patterns the network learned by adjusting connection weights between neurons. It worked as follows. He provided as input to a neural network a raw board description. It was the job of this middle layer to learn features or patterns of the game related to winning. Therefore, instead of using few human-designed features, it used thousands of machine-learned features averaged together. This middle layer connected to a final layer of output neurons which produced the value estimate of the board position. And the connections between these layers would adjust their strengths or weights during training. These weights determined how much each learned feature from the middle layer contributed to the final value estimate. Also, Tesaruo changed how rewards were defined compared to Samuel, because learning based on win-loss is difficult since you need to take so many moves before hitting your reward or punishment. And so he used a second breakthrough at the time to get an ongoing learning signal at each step. At a high level, here's the idea. At any point in the game, before taking your best move, measure the value of your current position. Let's say it's 80% chance of winning. Then you take your move and remeasure the value of the new position. Maybe it's now 90% chance of winning. Ideally, these numbers would match if your value function was perfectly accurate, but if they don't, you update your value function to nudge it closer to matching. Sutton described this method as learning from your own guesses, which are one step apart in time, which is why it's called temporal difference learning. But here's the key. This TD learning approach kicks in after the network plays through to an end game. These end states of wins and losses anchor the learning process. After a few hundred games played through to the end, the network gets better at predicting winning patterns one move away from end games. And so once it understands how to value board positions one move away from a win and loss, it starts to get better at predicting 2 moves away, and so on, all the way until it's able to accurately predict the value from the opening move. And so the value function learns how to understand game board positions backwards, from end games to opening games. This is known as bootstrapping. And after playing around 300,000 games against itself, it started to play better than human. He writes, "It seems remarkable that the neural networks can learn on their own how to play at a level substantially better than a computer system designed by the best experts. But how it played was most interesting to him. Its strength was in the middle game positions where judgment, not calculation, is key. That is, his neural network had developed intuition like the masters. and he wrote, "This has apparently solved the long-standing feature discovery problem, what Shannon had dreamed of." However, there was not an explosion of results after this publication, because researchers found that learning a value function on highly complex games and continuous problems in robotics was impossible, because the learning process would either not start, slow down dramatically, or even get worse over time. A key reason for this instability is that the value function is focused on position or state quality, not action quality. And so a key improvement needed was to train networks more directly on actions. This idea was proposed in a 1989 PhD thesis by Watkins. He suggested simply that instead of learning the value of a state, you should learn the value of a specific action in a state. He called this action quality, which he called a Q function. And this more targeted approach to learning often leads to faster and more stable results. A second key realization was that we needed to train these systems on much bigger neural networks. But this wasn't obvious until 2012, when a team built AlexNet, one of the largest and most complex neural networks of its time. This was building on LeCun's work, but instead they were trained to categorize images, which is an unfathomably complex task to human engineer. And exactly how Tesaruo saw LeCun's digit recognition networks and got inspired, the team at DeepMind saw this breakthrough and decided to follow up on the work of Tesaruo by applying Q learning and large neural networks, or what they called a deep Q network. Their goal was to create a single network to play as many games as possible, and it would only learn from the rewards it would get in the video game, such as points or winning and losing. It started from scratch, what we call a knowledge-free approach. And so they set up their network to receive an input from screen pixels, followed by 8 layers of neurons leading to an output neuron for each possible controller action. These outputs corresponded to the predicted Q value for each individual action. And in the same way, they initialized their network with random weights at first, so initially it would press random buttons and couldn't play at all. But after each experience, it would update the Q function to get slightly better at getting rewards. And they had it play millions of times across multiple games. And incredibly, it worked.
Now after 2 hours or 300 games, it's better than any human can play this game.
It was clear that this system could learn to play games by anticipating future rewards. And they showed this in their paper by looking at the network's action value estimates as it played Sequest. The figure shows that the predicted value jumps after an enemy appears on the screen. Then the agent fires a torpedo at the enemy, and the predicted value peaks as the torpedo is about to hit the enemy. Finally, the value falls to roughly its original value. They write, "This demonstrates that our method is able to learn how the value function evolves for a reasonably complex sequence of events." While this was an extremely exciting breakthrough, there was still a key limitation to this approach which prevented its direct application to physical robotics. AI could beat humans at chess, but nowhere close to washing dishes. Why? One key reason was Q learning can break down with continuous control problems where the action space isn't a choice between a few buttons, but a range of possible actions. One of the most important examples of this is the RoboCup, which started in the mid-90s and challenged robots to play soccer autonomously. And to this day, it represents an important benchmark for physical intelligence. The first systems that tried Q learning were promising, but noticeably brittle and clunky. That's because they had to break up the action space into a small number of chunks or buckets, like move forward, turn left 45 degrees, or kick. And so this approach to deep Q learning faced a key problem: how to handle large, continuous action spaces. A solution to this problem takes us back to the original Box's algorithm, which directly learned the probability of all next actions, but powered by a neural network, where a state would be provided as input, but for the output, it would be the probability across all actions, known as an action distribution. An unlearned policy starts as random with equal probability for all actions. And as it learns, the shape of this action distribution changes in the direction of more reward. And then the policy can simply select an action according to this distribution. And this approach can handle any number of possible next actions. This is known as a policy gradient approach. A key problem with this direct policy method is it's a much harder task. Since you're not learning values of individual actions, you're learning a distribution over all actions. And so generally speaking, it requires more experience to learn effectively. And because of this need for so much experience, most of the initial progress was in simulated robotics. Because with simulations, you could speed up time by orders of magnitude and get years of experience in hours. But that still left an open question. What about the physical world? Robots trained in simulation and then transferred to a physical robot would fail at complex tasks. And it was due to the complexity and unpredictability of the real world. And research aimed at training robots with direct policy methods entirely from physical experience with no simulation faced the frustrating challenge that it was much slower and expensive to do. And for the first few years, there were many hacks to try and make this work. For example, adding human-engineered rules such as preventing large changes to the action distribution at any step, as if elastics were attached to it, to stabilize it, known as proximal policy optimization. But a critical unlock came when it was realized that instead of more accurate simulations to learn in, you actually need less precise simulations. That is, you train a robot in purposely messy or fuzzy simulations. To do this, researchers simply trained a robot in simulation, but randomized all the key aspects of the simulation, such as gravity, friction, size, lighting conditions, to create a huge variety of environmental experiences to learn from. This approach, known as domain randomization, helped robots develop more robust and adaptable behaviors that could transfer better to the real world. A small research lab at the time, known as OpenAI, famously demonstrated this approach with the first physical, complex hand which could learn dexterous manipulation of a cube. The reward signal in this case was based on getting the cube into different orientations. And they trained this hand first in simulation and then transferred it to a physical robotic hand. They noted that the randomization provided a diversity of experiences it could draw from, and so it generalized over environments. This allowed it to recover from all sorts of things you could throw at it.
One thing that's very interesting to us is how general the system is. Not only can it rotate blocks, but it can perform tasks with other shapes as well.
It was very human. All of these were emergent behaviors, physical intelligence, which came out of the learning process. And if we fast forward to 2024, DeepMind has been working on robot soccer and applying everything we've learned so far. They've been training humanoid robots with direct policy methods in simulation to play soccer with domain randomization using scoring as a reward. After simulation, this neural network was then transferred directly into a physical robot with no additional training. And like the hands, they show complex emergent behavior that humans learn, such as anticipating shots, blocking shots before they happen. This was even more evidence of physical intelligence emerging from the learning process. The researchers visualized these learned behaviors as pathways through action space. A key next step in their work is including more in-life learning so the live robot can continuously improve. And so a key question they have is how much needs to be learned in simulation versus the wild. But there is an even deeper question lurking. All of the methods we've looked at so far are ultimately narrow systems. Their rewards were defined to solve a specific problem, not general purpose problem solving. And so what about general physical intelligence? A robot that can act in any way to do anything.
If you go back to ancient history of game playing AI, of checkers AI, chess AI, computer games AI, everyone would say, look at this narrow intelligence. Sure, the chess AI can beat Kasparov, but it can't do anything else. It is so narrow, artificial narrow intelligence. So in response, as a reaction to this, some people said, what we need is general AI.
So how do we fix this? Today, researchers are feeding robots millions of hours of human movement to learn from. But pure imitation is brittle, so we are giving the robot an imagination. These robots will simulate the next few seconds of action. In the same way a large language model talks to itself before responding, these robots will simulate the next 5 seconds of action before acting. But a simulation is useless unless you care about the outcome. By combining imagination with this synthetic pain, we give the robot the ability to feel failure before it happens. This closes the loop. 60 years ago, Michi's matchboxes learned by consequences. Today's robots will learn by watching us and then simulating those consequences in their own minds. But what does that mind actually look like? How do you build an imagination? Luckily, I've made a video which breaks down this history of machine reasoning. It'll force us to answer the question, what is the line between actions and words?
Look, Dave. I can see you're really upset about this. Will you stop, Dave? Stop, Dave. I'm afraid. I'm afraid, Dave.
Speaking of machines that can reason, this video is brought to you by Higgsfield AI and their brand new Nano Banana Pro engine. Unlike older image generators that struggle with details, Nano Banana Pro is powered by Google's Gemini 3 Pro model. That means it has actual visual reasoning, understands counting, anatomy, and can finally render perfect text inside images at high resolution. For example, here I asked it to render a robotic hand in DaVinci style with text labels, and it all actually makes sense. Right now, they're offering unlimited Nano Banana Pro generations for 1 year. This won't last, so click the link in the description and start creating without limits. Use my promo code and get access to all top AI models.